Section 1.5, Graphing Techniques and Transformations. In general, when we have a function, if you can put it in this form, now this form is very picky. That is, you have some coefficient outside the function. If it exists, it could just be 1, that's fine. You have some coefficient outside some x plus or minus c. You might have these values, b could be 1 and c could be 0, that's fine. D could also be 0. But this is just how the basic transformations can look. Well, the deal is that anything outside of the function is going to affect the graph vertically. And so notice that I have this f of all the stuff on the inside. So the outside stuff is the a and the d. Then when we consider stuff inside the function, that is the b and the c, that's going to affect the graph horizontally. Now to get it in this form, you must factor the coefficient of x out on the inside. So if there's some sort of number multiplying x, that has to be factored out from both things in this binomial. So first let's talk about a. A is outside. If it's outside the function, it's going to affect vertical things. Specifically, if it's minus a, this thing's actually going to reflect the graph over the x-axis, or turn it upside down. Then, if the absolute value of a is a number bigger than 1, we say absolute value of a because once you take care of the negative part, that is the reflection over the x-axis, you get to ignore it. And if the absolute value of a is bigger than 1, we're actually going to get what's called a vertical stretch. Specifically, it's going to stretch by some factor of a. Then, if the absolute value of a is between 0 and 1, that is, we really get to ignore the negative, then this is actually going to be a vertical compression, or it's going to shrink vertically by some factor of a. D, it's on the outside, so it affects vertical things. So what happens? If we add D, this thing is actually going to shift up by some D units. So it just moves up D amount. If we subtract D, it takes the entire graph and moves it down D amount. This B, which is really the coefficient of x, it's inside. Notice that it is inside the function. Since it's inside the function, it's going to affect horizontal stuff. Specifically, if we have negative B, this thing is going to reflect across the y-axis. That is, flip sideways. Then if I take the absolute value of b and I have it's greater than 1, that is, we ignore the sign on b, if that value is greater than 1, then this thing is actually going to compress horizontally. So this is actually backwards from what happens on the outside. Now, if the absolute value of b, that is b, we ignore the sign, is between 0 and 1, since it's backwards from the vertical stuff, this is actually going to be a horizontal stretch. Then considering C, it's inside, it affects horizontal. If we add C, because it's inside and horizontal, it works backwards the way we'd think. It is actually going to move this thing left by C amount. Whereas if we subtract C, since it's backwards, it's going to move it right some C amount. In general, this is the thing. Do all reflections first. Then do your stretches and compressions. Then translate. Translate moving up, down, left, or right based on C and D. Alright, so if the point 1,5 is a point on the graph of y equals f of x, what point must be on each of the following? Well, first off, if you want, let's do a visual representation to keep ourselves on track. That is, if I have this graph, the point 1,5 would be about right there. Then we just have to remember what these transformations are actually doing to that point. And so if the point 1,5 is on the function y equals f of x, then this function is going to reflect. When we see this negative here, this is a vertical reflection. And since it reflects vertically, what that means is it's going to reflect across the x-axis, which means that if it has to mirror across the x-axis, it's going to have to come up down here. And so if you want, visually, you can say, oh, well, I know that if I had the point 1,5 on the graph and then I reflect it vertically, the point 1, -5 must show up on the graph. And so that is on this function, 1, -5 must occur. Then, if we have y is equal to -1/8 f of x, we just have to remember what this thing does. This actually does two things. This negative is a vertical reflection. That is, it flips it across the x-axis. So I know that the point 1,5 is then going to be reflected. But then we have to say, what does 1/8 do? Well, 1/8 is actually vertical shrink. And once again, remember that's because if we have the absolute value of a between 0 and 1, we get a vertical shrink. And since it's affecting the vertical stuff, that means it's really affecting the y value. Y value is the vertical. So the vertical reflection changes the sign, just like it did above. So it's going to change from 1,5 to 1, -5. But then the 1/8 actually shrinks it vertically And so if you want, 1/8 is really the factor that we're going to multiply times that vertical component, or the y value, to get the correct y value. So 1/8 of 5 is just going to be 5/8. Do remember that it is negative due to the reflection, and so that is the point that shows up on the graph now is 1, -5/8. Then we've got to deal with y is equal to f of x plus 2. But notice that we're on the inside, and so this is horizontal, and it's a translation. That is, it's either going to move it left or right, but because it's plus, it actually moves left 2. And so then we go back to our initial value, and if we had 1, 5 here and we moved it left 2, 1, 2, it would move over here to -1, 5, and we know that that value would then have to be on the graph. And so I just took the -2 from 1 to get 1 minus 2, which is -1, and that is the value -1, 5. So now let's write the function. Now let's write the equation for the function y equals absolute value of x that contains each of the following characteristics. So let's say we want to shift it up 2 units. Well, if I want to do that, that's really going to be the function y equals up 2 means on the outside I add 2 of the function. So that's going to be the absolute value of x plus 2. That's how I would shift up the entire function 2 units. If I want to shift it left 3 units, this is horizontal stuff, so it's got to be on the inside of the function. So that's going to be y is equal to the absolute value of x. Left 3 is actually plus 3, all in absolute value. Once again, horizontal is inside the function. Then if I want to shift the function right 4, and I want to reflect it over the x-axis, 2 things have to happen. First off, I know that shifted right 4 units, that's inside the function. So y is going to be equal to the absolute value of x. Right 4 is really -4. But if it's reflected over the x-axis, that's a vertical reflection. This is going to have a negative on the outside. So my y equals negative absolute value of x minus 4. Now let's say I want to stretch it horizontally by a factor of 10. Notice that this is a stretch, and so because I've said stretch, this is going to be y is equal to the absolute value of multiply by some factor of 10, but stretch horizontally actually means that it's got to be a number between 0 and 1, or 1/10 times x. Now if I want to stretch vertically by a factor of 2, shift right 1, down 5. So we're doing 2 things with the vertical stretching and reflecting, that is reflect over the x-axis and stretch vertically by a factor of 2. So I'm going to multiply the entire function by -2. Stretching vertically, the numbers need to be bigger than 1 in absolute value. Then multiplied by the function, x, and this is going to shift right by 1, so that's -1, and then it needs to go down 5, and so on the outside, that's going to be -5. We want to describe the graph of the following function, and then we're going to use 3 key points to graph the function and state its domain and range. So first off, from our library of functions, this is a squared function. So it is quadratic, it is a parabola. Then ask yourself, what do these things do? Well, this is on the outside of the function, so it's actually going to be a parabola that shifted down 5 units. So then, if I were to consider some original points to start by graphing, I would probably pick -1, which would give me 1 when I square it. I would pick 0, that 1 squared gives me 0, and I would pick 1 when squared is 1. And then when I transfer these things, I'm just moving these values down by 5. And so that is, the new points will actually be -1, -4, 0, -5, and 1, -4. And if we want, we can then graph this. If you wanted to plug those values in, that's really where I got them. -1 squared is +1 minus 5 is -4. 0 squared is 0. -5 is -5. 1 squared is 1 minus 5 is -4. And so I can actually graph this function. That is, the origin point is going to be shifted down 5 points to 0, -5. And then those other points I found that were originally on the parabola -1, 1 get shifted down by 5 units. That's here and here. And so now I have the parabola that looks close to this. Now I'm sketching very quickly, so I make no claims that any of my other points are correct other than the 3 dots that I've got. But because I've got the correct shape, because it's a parabola, it's close enough for us. Now, when we want to talk about the new domain and the new range of this thing, first off, what is the domain? Well, the domain of x squared minus 5 is going to be all real numbers. That is from negative infinity to positive infinity. The range here, start from the bottom, move your way up. First values on the graph occur at negative 5. It does exist, so it gets a square bracket, and then we continue to have points all the way up, and so that goes up to infinity. Let's try it again. We want to describe the graph of the following, and then we're going to use 3 points to graph the function and state its domain and range. So first things first, remember what the square root function looks like. Well, the square root function unchanged looks like this. Well, then let's discuss what changes actually occur. Well, 2 occur. That negative is a horizontal reflection. That is, it's going to turn the entire graph sideways. Then notice that we have this minus 4, and this minus 4 is on the outside of the function, so it's going to shift down by 4 points. So remember that on the original function, the original square root function, we had 0, 0, and then some nice easy ones to calculate. 1, so we had 0, 0, the origin point. And then if we plug in 1 into just the square root function, we're going to get 1 because the square root of 1 is 1. Then if I want to plug in another nice value, how about we plug in 4 because the square root of 4 is really 2. Once again, remember for the original, I'm really just pretending that I have the original function square root of x. Then I need to transfer this function using this horizontal reflection, and I need to move it down 4. So a horizontal reflection flips it across the y-axis, and then it's going to shift down by 4. Well, if I flip the x-axis across for 0, it's still 0. Then I could just save time and plug it into this function, or I can realize that I'm shifting it down 4, and it's going to give me minus 4. Let's confirm that calculation is correct. Negative 0 is 0. The square root of 0 is 0. 0 minus 4 is negative 4. Perfect. Then, if I have 1, and this thing flips across the x-axis, I know that it shifts over to negative 1. Well, then I also need to move the value 1 down 4 points to give me negative 3. Let's plug in negative 1 to confirm we get negative 3. Negative 1 times negative is positive 1. The square root of positive 1 is 1. 1 minus 4 is negative 3, and so we're good. Then let's pick our other value. We've got 4 here, but 4 horizontally reflects. That is, it's going to give us the value negative 4. Then, because it shifts down by 4 points, 2 minus 4 is going to give me negative 2. Let's confirm that negative 4 gives me the correct value. Negative 4 times negative 1 is 4. Square root of positive 4 is 2. 2 minus 4 is negative 2, and we're good. But then, remembering that this was my original function, my transformation reflected it and then pulled it down 4 points. That is, my origin point is here, and then if you wanted to plot the points we found now, negative 1, negative 3, negative 4, negative 2, and this is our function. Once again, I only claim that my points that I've plotted are correct. The rest is just a sketch. But now that we've changed this, what's our new domain? Well, because this function goes all the way to the left, our new domain starts at negative infinity and goes all the way up to 0. That value does exist, so it's included with a square bracket. Then for the range, we move from the bottom, and the first value we get is negative 4. So negative 4 gets a square bracket, and then it continues up forever, and so it goes to infinity. Now let's take a look at what graphing on MyLabs looks like. So let's graph this function. And so we're going to use those techniques that we just talked about to save ourselves some time. So first off, notice what our library of function gives us. What is our parent function? That is going to be the absolute value function. And so if I want to graph the absolute value function, I know that this thing looks V-shaped. So I'm going to pick the V. Then I consider what's being said here. This 3 here is telling me that it's actually a vertical stretch by a factor of 3. I also need to be a little bit careful because inside this absolute value, this isn't in the correct format that I would like. And so let's adjust that. What I would really like is f of x minus or plus c. So let's get this in the right format. That is g of x is equal to 3, which matches up to our a. Then we want to rearrange the inside so the x is out front. So that's going to be negative x plus 4. Then if you look at your notes, remember that b is that coefficient of x, and so we need to factor it out. So that is, this is going to be 3 times negative 1 times x minus 4, and now we have 1, 2, 3 changes occurring. This is a vertical stretch by a factor of 3. This is not a stretch or compression because it's 1, but it is technically a horizontal reflection. That is, it turns sideways. Then we have this minus 4 on the inside, so remember that that's shifting left or right, but it's backwards, and so negative is actually right by 4. And so this whole function is the v shape for absolute value, stretched vertically, and the point is shifted right 4 units. Now because it's shifted right 4 units, it's probably a good idea to use a t-chart to find nice things, but the way we're going to pick these values is, since we shifted right 4, the x value that we want to pick at the center is going to be 4. Then we're going to pick a value to the left and a value to the right. And so how about we pick 3 and 5? Then I'm going to plug them into the function. That is 3 times negative 1 times x minus 4. And that's going to give me 3 minus 4 is negative 1. Negative 1 times negative 1 is positive 1. Positive 1 absolute value is 1. 1 times 3 is 3. Then calculate 4 minus 4 is 0. 0 times negative 1 is 0. The absolute value of 0 is 0. 0 times 3 is 0. Then plug in 5. 5 minus 4 is positive 1. Positive 1 times negative 1 is negative 1. The absolute value of negative 1 is positive 1. And positive 1 times 3 is 3. So then notice that if I try to graph this function, I see that it's the v shape, and so I'm going to plot these points that I've found. So I'm first going to plot the point 4, 0, just by choice. Then I need to pick the other values I found. So I need to plot the point 3, 3. Notice that it's getting taller and skinnier because vertical stretch. And then actually this one ends up being done. We don't even need to plot the third point, but notice that the other value, 5, 3, also showed up on the graph. Then we're done. Let's try another one. Notice that first our library of function tells us that this is a cubic function. So since it's a cubic function, if you want, you can go ahead and do a quick sketch. I know that somehow it's got to look like this. But then I need to write out the function and make sure that it's in the correct form so that I can figure out what transformations actually occur. Well, I've got negative on the outside. That's actually going to be a vertical reflection. And then I've got x plus 1 quantity cubed. Notice that there's no coefficient of x, which is good. If there was any coefficient of x, we'd need to factor that out first. And then minus 3 on the outside, that's going to move it down 3. So down 3. Plus 1 on the inside is backwards, so that's left 1. Then I have the negative here, which is actually a vertical reflection, or upside down. So it's flipped upside down. Now if I want to graph this, I'm going to use a t-chart to make sure I have everything I need. So then remember that because this thing moves left 1, remember that that point was the point on the origin of the original function, and since it shifts left 1, I want to shift the origin left 1, and I'm going to use the x value minus 1. That's where I'm going to center everything. Then I want to pick a value to the left here and something to the right. So a little bit to the left of negative 1 is negative 2, and a little bit to the right of negative 1 is 0. Now I'm just going to plug these values in. Negative 2 plus 1 is negative 1. Negative 1 cubed is negative 1. Negative 1 times negative is positive 1. Positive 1 minus 3 is negative 2. Then I have negative 1 plus 1, that's 0. 0 cubed is 0 times negative is 0 minus 3 is minus 3. Then I plug in 0. 0 plus 1 is 1. 1 cubed is 1. 1 times negative 1 is negative 1. Negative 1 minus 3 is negative 4. Now I'm going to plot this cubic function. And because of the way MyLabs graphs these cubic functions, I won't actually have to use those points that I found. But if I were graphing on paper, those points would be perfect. Now I just have to type in the information that I've already found. I know that this thing flips upside down. That's a reflection across the x-axis, so I check that box. Then I know that this thing moves left by 1. So I move this to the left by 1. Then I know that this function shifts down by 3, so I shift it down by 3, which is minus 3. And notice that if we wanted to check against what we've already found, the point negative 2, negative 2 does appear on the graph. So does the point negative 1, negative 3. So does the point 0, negative 4. And so we have actually graphed this function. We save it, and we're good. Let's try another. We have the graph g of x is equal to 5 times x minus 4 quantity squared plus 3. Let's check to make sure we're in the right format. Notice that we have no coefficient of x, just a 1, which means that we're perfectly fine there. Then let's answer the question about what happens here. This 5 is a vertical stretch. Then we have on the inside this minus 4, that's a horizontal stuff, but specifically it goes right 4. Then I have this plus 3 on the outside, that is up 3. Then if we wanted to pick some points to plug into our function to double check our values, we could always pick some values. First we should find our middle. Our middle is going to be right 4, so 4. Then let's pick something to the left of that. How about 3? And something to the right of that, how about 5? Then I'm going to plug this into the function. 3 minus 4 is negative 1. Negative 1 squared is positive 1. Positive 1 times 5 is positive 5. Positive 5 plus 3 is 8. Then 4 minus 4 is 0. 0 squared is 0. 0 times 5 is 0. Plus 3 is 3. Then 5 minus 4 is 1. 1 squared is 1. 1 times 5 is 5. 5 plus 3 is 8. So if I were graphing this on paper, I would now have enough to get a good sketch. But let's graph it in MyLabs. Remember that from the library of functions, this being squared means that we do have a parabola. So I need to select the parabola, the U shape. Then when I click something on the graph, it allows me to enter all of the translations that we've already done. Specifically, we know that we have a vertical stretch of 5. So I do a vertical stretch of 5. I know that we don't have any reflections, vertical or horizontal. We don't have any horizontal stretches or compressions because we don't have a coefficient of x. We did shift it vertically, specifically we went up by 3. Then we have a horizontal shift and we went right 4. Then let's double check ourselves. We found the point 3, 8. So notice that 3, 8 is a value on the graph. Check 4, 3. 4, 3 is a value on the graph. And 5, 8 is a value on the graph. We're good. We have found our function. Click Save. We're done.